Good day, students. Welcome to class. Today, we will be dealing with Hooke's law under the topic forces and matter. So, as seen in chapter 5.2, when the load on a spring is doubled, the extension is also doubled. This shows that extension depends on load. With that, let's do this activity. If a spring, is that so? We'll check and see later. If a spring is stretched beyond limit, it will be permanently damaged. If a load is removed, the spring will not return to its original undeformed length. Can we check? That's correct. Now, the extension versus load graph is illustrated below. For a spring stretched beyond its limits, the behavior of the spring is known as Hooke's law. When we are dealing with extension in relationship with a load, Hooke's law covers the region that is from the 0 point towards the black dot. Any region beyond the black dot indicates that the spring in question that is being used for demonstration has been deformed. Let's move on. Now, let's drag the following word into the correct boxes to be able to state what Hooke's law is. Now, Hooke's law states that the extension of a spring, as we saw earlier, is proportional to the load or force applied to it, provided the limit of proportionality is not exceeded. So let's check and see. That's correct. The Hooke's law can also be written as an equation. That is, F is equals to Kx. F is the load or the force. K is the constant or proportionality, or we can call it stiffness constant, while X is the extension. And don't forget what the extension denotes. Extension is what? The length that we have minus the original length. That is extension. That is associated with the spring. Now, let's solve these questions. A spring has a spring constant K is equivalent to 20 Newton per centimeter. What load is needed to produce an extension of 2.5 centimeters? We already know that F is equal to Kx. Now, our K is equal to what? F over X, or our X can be written as what? F over K. But here, we are asked to look for load. Our load is now what? F. F now is equal to, what's our spring constant? 20 Newton per centimeter multiplied by the extension 2.5 centimeter. So we now have 20 times 2.5 can be written in improper fraction as 5 over 2. So force is measured in newtons. So we have this, that's 10, that's 10 times 5, that gives us 50 newtons. Is 50 newtons part of the options? That's true. So let's pick it and see. That's correct. Now let's move on. A spring requires a load of 2.5 newtons To increase its length by 4 centimeters, the spring obeys Hooke's law. What load will give it an extension of 12 centimeters? Now, let's solve it out before we pick the answer and follow the solution one step, then the other. A spring requires a load of 2.5 newtons. That means F is equals to 2.5 newtons. To increase its length, that is X now, is 4.0 centimeter. What load will give it an extension E of 12 centimeter? So we want to know the F that is associated with E. We know the F that is associated with X. But at first, we know F is equals to what? Kx. So let's find the stiffness constant K. That is F over X. K now is equal to 2.5 or divided by 4. So we can write our decimal, this is 2.5 in terms of what? Fraction. That's 5 over 2 divided by 4. And that gives 5 over 2 times 1 over 4. So K now is 5 over 8. It's 5 over 8 Newton per centimeter. So if I should have F now for the extension is equals to K now, the extension multiplied by the extension itself. First, in relationship with the extension now gives 5 over 8 times the extension of 12 centimeter. So 4 here, that's 2. 4 here, that's 3. 5 times 3, that's 15 over 2 in newtons. That gives 7.5 newtons. Do we have 7.5 newtons? Let's pick and see. That is correct. All right, let's proceed. A spring has an unstretched length of 12 centimeters. Its spring constant is 8 Newton per centimeter. What load is needed to stretch the spring to a length of 15 centimeters? Now, this is a little different from the former question. We have an unstretched length of 12 centimeters, that is what? L naught, 12.0 centimeter, and we have stiffness constant or spring constant to be 8.0 Newton per centimeter. They're now asking for load, F. We don't know the value yet. Then, to stretch the spring to a length of 15 centimeters, that means L is what? 15.0 centimeter. Don't forget our X here is equal to what? E, which is what? L minus L naught. Then 15 minus 12, all in centimeter, gives what? 30 centimeter. And our general formula is what? F is equal to KE. F now is equal to spring constant of 8 Newton per centimeter multiplied by extension of 3 centimeter. First is measured in newtons. So F now is equal to 24 newtons. Do we have it as part of our option? Yes. So let's pick it and see. That's correct. So we move on to how rubber behaves. A rubber band can be stretched in a similar way to a spring. Using a spring, the bigger the load, the bigger the extension. If adding weights with great care and removed one by one without releasing the tension in the rubber, the following phenomena is noticed. A. The graph that will be obtained is not a straight line graph. It will not obey Hooke's law. B. Increasing the load does not produce any extension. The rubber becomes stiff. When the load is removed, the graph does not come back exactly to 0. This is illustrated below. We have a graph of extension against load. When this particular rubber is loaded, it won't at all obey Hooke's law, so it won't return back to zero from the initial point where it's starting from. So with that, let's deal with some activity. Now, looking at this diagram above, looking at it, we can see that this is a spring. Now, what does the question say? Springs are used in the production of plastics. Plastics and springs does not have a common material. How about rubber? No. Wristwatch consists of springs. Then weighing machine, yes, weighing machine consists of springs. So we have wristwatch, we also have weighing machine. So we check. That's correct. Now we've come to the end of today's class, but we won't go without having what is known as summary in terms of us checking the correct statement. So let's analyze the statement one after the other. If a spring is stretched beyond limit, it will be permanently corrected. That statement is wrong, because when a spring is stretched beyond limit, you don't expect it to be permanently corrected. It will have been what? Become useless. If a spring is stretched beyond limit, it will obey Hooke's law. No, this statement is false, because Hooke's law only comes into play when there is relationship between extension and what? Force. And when a particular spring or force is much more what? Loaded beyond normal, it what? Becomes permanently damaged. It becomes inelastically unuseful. So if a spring is stretched beyond limit, it will be permanently damaged. So this is the correct statement. Thank you for your time once again. Do well to visit our website www.edubbey.com for more of our interactive notes and class. Thank you for listening.